Hello, my name is Yetli Rosas Guevara, and this is the long version of my talk. Today I'm going to talk about the properties of void galaxies under black holes in the Eagle simulation. This work has been in collaboration with Patricia Tisera, Enrique Paillas, Nelson Padilla, and Claudia Lagos. Let me start with a brief motivation about the role of the environment in galaxy evolution. And if you compare two galaxy populations living in different large structures, the galaxy properties are different. This plot illustrates the luminosity function for different environments, clusters, which are dense environment in comparison with underdense regions that is called voids, and I will talk later about this. And you can see that the luminosity functions are different. It has been found that low mass galaxies, bluer galaxies, and with late up morphology are more common in underdense regions than in denser environments. But if the galaxy properties are affected by environment, one expects also that the black holes residing in them have grown differently, especially if the triggering of the AGN activity is associated with external physical processes such as galaxy interaction, ram pressure stripping, tidal forces. From the observational side, there is evidence that the AGN activity is higher in under these regions. In particular, Constantine, based on Sloan data, found that the strong AGN, the fraction of galaxies with a strong AGN is higher in massive galaxies in comparison with wall galaxies. This is shown in the top panel of the figure. But the fraction of galaxies hosting moderate luminous AGNs is smaller or equal in voids than in denser environment. So all of these results, taking into account, our goal is to determine how the environment has affected the mass assembly of the galaxies, and also understanding how galaxy properties under black holes depend on the large scale environment. For that, we use the Eagle project, which is a suite of hydrodynamical cosmological simulations. The simulation includes subgrid physics of galaxy formation, such as star formation, metallicity-dependent gas cooling, black hole physics, supernova, and AGN feedback. The subgrid physics has been calibrated to match the low redshift observables of a galaxy population. In particular, we use the largest simulation, which has a volume of 100 megaparsec cube and run from redshift 127 to redshift 0 and a mass resolution of 10 to 6 solar masses. And the Eagle project has widely used in the community to understand the properties of the galaxy populations. Let me talk a bit about cosmic voids, which are under these regions in the cosmic web. They account for more than half of the entire volume of the universe, and they are typically used for cosmological constraints. They are important because are ideal to understand the role of the large scale environment in the galaxies, since because they are under these regions, they are not subjected to physical processes that act in more dense environments. We use the void catalog from Paillas et al. 2017, which is based on identifying spherical underdensities in a galaxy distribution, and the voids are characterized by the center and the size. The catalogue of Paillas consists of more than 100 voids, more than 700 voids, with sizes ranging between 3 and 25 megaparsecs. We have central galaxies with a stellar mass larger than 10 to 9 solar masses, and the final catalogue results in more than 7,000 galaxies. We split our final galaxy catalog into 4 samples based on the relative proximity to the closest void, relative to the size of the void. We define these regions as inner void galaxies, outer void galaxies, wall, and skeleton. And this visualization of the stellar mass of the dark matter distribution of the simulation shows how well defined are our samples, which are the points with different colors. For instance, wall and skeleton galaxies lie in the thin filaments of the dark matter distribution, or in the dense regions, whereas inner and outer voids are located in the under these regions in the simulation. As we expected, the stellar mass distribution of inner voids and outer voids galaxies are biased toward lower mass galaxies, and then skeleton and wall galaxies that present a median stellar mass higher in comparison with the galaxies that are located in inner and outer voids regions. The fraction of star-forming galaxies as a function of the distance to the closest voids is shown in the left panel of the slide. So you can see that the star formation activity is higher in inner voids and decreases as we move to denser regions. This is something that has been also observed for Richard Daly using the SLOAD, where they found that the star-forming galaxy fraction decreases as well as as increasing the distance to the center of the void. However, this decreasing trend could be caused due to the overabundance of low mass galaxies in voids, and in order to separate the effects of the stellar mass, we define subsamples with the same stellar mass distribution as the inner void galaxies. In particular here, I will show my results from the inner void galaxies and the skeleton galaxies just for clarity reasons. However, we explore all the regions and all the galaxy properties that we can. Here, I only show the main results. And let me start with a specific star formation rate stellar mass diagram. From the plot, you can see that the specific star formation rates of the inner voids, which are blue lines in average, is similar to the specific star formation rates in skeletons, except for the low stellar mass galaxies that there is a weak tendency of the inner voids galaxies to present higher star formation activity. The Quenched galaxy fraction as a function of the stellar mass is illustrated in this plot, and it shows that inner void galaxies present less fractions of quenched galaxies in comparison with the skeleton galaxies, except for the 10 to 10 solar masses. And this is something that is expected from under these regions. An important property that characterizes a galaxy is their average metallicity. since it encapsulates the assembly history of a galaxy. The left panel shows the mean relation of the star-forming gas phase metallicity and the stellar mass. So we can see that inner voids in low mass galaxies present lower gas phase metallicity in comparison with the skeleton. We found the opposite trend for the most massive galaxies, where massive galaxies in voids present higher gas phase metallicities than a skeleton. However, here the scatter of the relation is higher. We also investigate the cumulative distribution of star-forming gas phase metallicity gradients, and we find that inner void galaxies present negative metallicity gradients more often than a skeleton, and we explore for two different stellar mass beings. Metallicity gradients are associated to the distribution of the metals, and if the metallicity gradient is negative, means that the central abundance of the galaxy are higher in comparison with the outer skirts of the galaxies. And if they are positive, we have the opposite effect. The central abundance are smaller in comparison with the outskirts. And positive metallicity gradients are associated with external processes such as the galaxy interactions, gas pressure, ram pressure stripping, and tidal forces. And the fact that we found some differences in the distribution of the negative metallicity gradients is an indication that the assembly history of the galaxies in inner voids is different from the skeleton galaxies. In the case of the AGN activity, the galaxy fraction with active black holes is higher in comparison with the skeleton. We test this with different volumetric luminosity codes, but also with Eddington ratio codes. Remember that the Eddington ratio measures the activity of the black holes. So for black holes with higher activity levels, well, we found that these differences, this excess of AGNs is higher. With Eagle, we have the advantage to explore the assembly history of the galaxies, and we find that if we stack the mass-weighted age distribution of the stellar populations, we can have information of the star formation histories of the galaxies. We find that massive galaxies in voids form earlier than in a skeleton. However, we don't find any difference in the age of the stellar populations for lower mass galaxies. We also explored the black hole evolution for the different stellar mass beings, and we see also some differences in the black hole growths of the galaxies that lives in inner voids regions than in a skeleton. In particular, we found that the black holes residing in low mass galaxies are formed later in inner voids than in skeleton galaxies. This is something important because, as we noticed previously, there is no difference in the assembly history of the inner and skeleton voids. However, in the black holes that they are hosting, the black holes that they are hosting, we see a difference in the growth of the black holes. Just to finish, let me give a summary of my results. Remember that all the results that I show here is using the same stellar mass distribution as the inner void galaxies, but in different large-scale environments. So we found that galaxies in voids are more star-forming. Low-mass galaxies in voids are less metal-rich than in a skeleton. Galaxies with AGN activity are more common in voids than in a skeleton. And when we explore the assembly histories and the black hole growth evolutions, we found that the massive galaxies in voids form earlier than skeletons, and black holes are formed later in voids. In summary, here for this work, we use a cutting-edge cosmological hydrodynamical simulation, which is EAGLE, and has shown that can be used to study the effect of the large-scale environment in the galaxy population. Thanks for listening, and any questions, you can email me at jetrock@gmail.com or also on Slack.